You want me to go ahead and start sharing my screen?
Oh yeah, sounds good. So let me introduce Professor Panagou first from myself. Professor Panagou acquired PhD degree from University of National Technical University of Athens, and she did a postdoc in the UIUC and the visiting research at the UPenn Grass Club. And she's a recipient of the NASA Early Career Faculty Award and the Air Force Office of Science and Research Young Investigator Award, and of the NSF Career Award as well. So yeah, we would like to welcome the first invited talk by Professor Panagou.
Thank you very much.
Please get started.
Can you all see my screen?
Yes, yeah, it looks good.
Okay, so that's the slideshow presentation, right? That's the slideshow mode.
Yeah, slideshow mode.
Okay, good. So I guess can go ahead and get started. Good morning, good afternoon, everyone. Thank you for inviting me to this workshop. And today we'll be talking about control synthesis for safety critical and time critical systems under uncertainty, which is joint work with my students Kunal Garg, Hassan Arabi, and Mitchell Black. So to motivate the theme of the presentation, I thought to start with the introductory video of Michigan Robotics that shows all kinds of robots in various types of environments, from aerial robots to ground robots to robotic manipulators to bipedal robots, operating in order to accomplish their missions safely in environments that they might not know a priori, or they might partially know, and they have to learn on the fly. And still they have to accomplish all these tasks with information about the environment that they have to learn on the fly, and while meeting safety specifications. And to add more excitement about uncertainty, I thought to include also the videos from Perseverance and Ingenuity that shows that we have robots operating on another planet. So I think it's important and evident that safety, maintaining safety in uncertain conditions is of paramount importance, because when this is not done and things are not carefully designed, then things can go wrong. So for example, a simple change in the payload can make a drone plummet from the sky, or not carefully safety design of the intersafety distance can make quadrotors collide with each other, or not safety specifications not being met can make a rocket landing go really bad. So planning and control at an uncertainty is a long-standing topic within robotics, artificial intelligence, the controls communities. And in order to keep discussing about that with a small or a simple case study example, let's consider that we have a quadrotor or an aerial robot that has to navigate in an environment, an urban environment. So there are obstacles, like physical obstacles, the buildings. There might be other quadrotors navigating also around. And it also has to navigate in the presence of processes like, for example, wind. So the quadrotor has imperfect information about the environment through its own a priori knowledge and its own sensory information. And it has to make decisions on, for example, whether it's safe to go through this path, or it should be better to go around the obstacles, in order to be so that it safely it keeps safe distance with respect to the obstacles, and using information about the wind that it doesn't directly measure, so that it has to estimate on the fly. So so that creates a problem of safety under uncertainty. And the questions, some of the questions that are related to this problem would be how we can ensure that the system trajectories will always remain safe in an unknown environment, in an environment that we might not know exactly the location of the obstacles, or the wind that is affecting the motion of the vehicle. How we can reduce uncertainty while staying safe. So maybe we can start learning models of the uncertainty, but how we can build better models on the fly while still staying safe. And how we can learn this uncertainty, these models of the environment in given time horizons that also meet the safety specifications. So sometimes we don't have abundant time in order to make a decision. We have to be able to act fast. And as a control theorist, I'm more biased towards the approaches where we can assume that we have a portion of our environment and the model that we can assume that we know with reasonable confidence. And then anything else that is more difficult to model or measure is usually lumped into a parameter D, okay, the disturbance D. So essentially the question is, what can we say about this D and how we can handle it in order to maintain safety? So I'll start my talk with the simpler case of considering no disturbances and still using the quadrotor moving among obstacles as a motivating example. And I'll describe how we can encode safety as set invariants. That's a well-developed approach throughout the years by many people working in the area. So the quadrotor has a safe set of states in which it is allowed to visit. So essentially, safety can be cast as a set invariance problem, or how we can make the state trajectories always remain within this safe set of states. And in addition, I will consider timed specifications as one of our performance objectives. So the quadrotor does not merely need to go from initial point to a goal point, but also needs to make sure that it will visit certain waypoints in between within given time horizons. So in the first part of the talk, I'll describe our framework on spatiotemporal control synthesis that relies on quadratic programming and merges safety encoded as control barrier functions and the timed reachability objective by means of fixed time stability notions. That is a novel construction that we have been working on. And in the second part of my talk, I'm going to describe our ongoing work on how we can extend this nominal framework to account for disturbances in robust adaptive control settings, and our thoughts about how we can further integrate more sophisticated learning techniques into this framework. Okay, so to get started with some preliminaries, so safety, as I already mentioned, can be thought as a forward invariance of a safe set problem. So we consider that we have our nonlinear control affine dynamical system, no disturbances for now. And let's assume that the safe set is given as the sublevel set of a constraint function H sub S. And the objective is essentially for trajectory starting within S sub S to never escape the set. So forward invariance has been characterized within the controls community through the so-called Nagumon's theorem that gives the necessary and sufficient conditions on set invariance. So in the notation that we are using here in this slide, the set S sub S is forward invariant if the following condition here holds. So this condition is nothing but the time derivative of the constraint function along the trajectories of the system, with all the assumptions that the trajectories are unique and exist in forward time and so on. So essentially, we impose that H dot is smaller or equal than 0 for all points in the set. Essentially, that boils down to checking the points on the boundary of the set. Okay, so so you want to be at the place where H S sub S takes negative values. So all it takes is to check whether on the boundary the closed loop vector field points to the interior of the set. Okay, so H dot smaller or equal than 0 for this notation. So then people have developed the concept of a control barrier function. So now our function H sub S is called the control barrier function for this system dynamics and for the set S sub S if there exists an extended K class K function A such that, again, we can choose a control input. This condition holds. Upon the choice of a control input, we can render the time derivative of h to be upper bounded by this negative quantity here that tends to 0 as the trajectories approach the boundary. Okay, so essentially, a control barrier function is a sufficient condition on ensuring set invariance. The trajectories are allowed to evolve within the set. They're allowed to approach the boundary of the set, but they are penalized from penetrating the set. Okay, so we can use control barrier functions in order to encode safety. In order to encode the time specifications that I mentioned earlier, let me give a brief overview of the notions of finite time and fixed time stability that we have utilized. So finite time stability is a stronger concept than exponential and then asymptotic stability, in the sense that the time of convergence to an attractive equilibrium is no longer asymptotic with time, is no longer infinite, but rather is finite. And in fact, the notion admits very nicely upon characterizations. So if we have a nonlinear system for which we can find a positive definite function v such that this condition here holds, then the origin is a fixed time stable equilibrium with a settling time that satisfies here this upper bound. Okay, so you see that the time of convergence is now finite and in fact depends on the initial conditions. You also notice that essentially everything boils down to tuning this parameter, this exponent vita here, which must be between 0 and 1. If vita is equal to 1, we recover the classical definition of asymptotic of exponential stability. So building upon this notion, fixed time stability is an even stronger notion that additionally dictates that the time of convergence does not depend on the initial conditions. Or in other words, the time of convergence is uniformly bounded with the initial conditions. So now if we have a positive definite function for our system such that this condition here holds, where notice that we just have another term here with the exponent now being greater than 1, then the origin is a fixed time stable equilibrium with a continuous settling time that satisfies now this upper bound. Okay, so now we can guarantee that the trajectories all converge to the origin within this upper bound that does not depend on the initial conditions, but rather depends on the parameters of the system. Okay, so with these preliminaries, let me describe again abstractly the problem that we have at hand. So we are considering that we have our nonlinear dynamical system. We consider a safe set as a sublevel set of a constraint, of a safety constraint function. We consider a goal set as the sublevel set of a goal set function. We define them such that their intersection is not empty. And the problem that we want to consider is how we can design controllers that are also constrained themselves by bounds that meet this form, such that trajectory starting everywhere in the safe set never escape the safe set and converts to the goal set for a user-specified time tau bar. Okay. So it's the appearance of it's the explicit consideration of input constraints that makes this problem interesting, because otherwise it would be straightforward to just use the fixed time stability result. So in order to encode this time convergence specification, we got inspired by the well-known control-Lyapunov function concept, and we defined the notion of a fixed time control-Lyapunov function, where we are defining it to be a positive definite function with respect to a goal set SG, meaning that it is a function that is positive outside the set and 0 on the boundary of the set, whose time derivative upon the choice of a control input is satisfying this condition 2 here. Okay, so you see here that this right-hand side term is nothing but the term that we get from fixed time stability. Okay, so with also all the parameters chosen properly to abide with the fixed time stability requirements, and with the upper bound being smaller than this tau bar, which is our user-specified time. So in simpler words, what does that mean? That means that if we can find the fixed time control-Lyapunov function for a given system, then we know that there exists a control input that can take the state trajectories to the goal set within a finite time that can be set to be smaller than this tau bar that has been set by the user. Okay, so that's our way of encoding the time specification. And now trying to think again of the overall problem of designing trajectories that stay within the safe set, never escape the safe set, and hit the goal set within our user-specified time. We can pose the following optimization problem that tries to minimize for the control effort and the slack variables, delta 1 and delta 2, that I'll explain why we have them here, subject to the three specifications: safety, time convergence, and input constraints. Okay, so C1 is the first constraint of our problem, which is nothing but the imposing of the control barrier function condition for forward invariance of the safe set of our safe set. The second condition imposes the fixed time requirement, the fixed time specification with respect to the goal set within a user-specified time tau bar. And in fact, it is a relaxed version of it, in the sense that whenever all these three conditions cannot be met, we decide to drop the time convergence specification for the sake of maintaining safety. Okay, so if we need to prioritize between the two specifications, safety is most important, we drop the strict time requirement for convergence. And C3 is obviously the control input constraints. So in fact, now the choice of these slack variables are shown I guess the definition of these slack variables within our problem setup can be shown to ensure feasibility of the quadratic program, in the sense that assuming that a safe solution does exist, so we can render this safe set a forward invariant set upon the choice of a constraint control input, then we can show that we can always find delta 1 and delta 2 that will provide a feasible, such that the quadratic program generates a feasible control input. In fact, this delta 1 in particular dictates the region D of fixed time convergence for the goal set. The D here set represents what are the set of initial conditions under these input constraints for which the trajectories are able to hit the goal set within the user-specified time tau bar. Okay, so now the sublevel set of this D set that is completely enclosed within the safe set is essentially the set of initial conditions from which safety time and input constraints can be met. And the nice thing is that all these D and DS sets have an explicit characterization, explicit forms in terms of the level sets of the fixed time control Lyapunov function that we have chosen, which is in that case is the constraint function, the goal constraint function. So the representation are rather long and tedious, so I'm going to skip those. But let's see how this quadratic program would perform for the simple case of aerial patrolling. So here we have two robots that they need to navigate within this square, but staying outside this circle, and they need to move from corner to corner no later than a given time horizon, which is given as 1 second in this simulation example. So the traced paths demonstrate that the safety requirements are met, also shown, evidenced also here for the interagent distance from this figure. And also we can see that indeed the control input bounds are met for the closed loop trajectories of the system. And also that the time specification is met because the control input goes to 0, and the vehicle essentially stops whenever reaching the goal set way before the time horizon, that the imposed time horizon. Okay, so that was the nominal construction, relatively easier than the case of considering disturbances. So now, if we want to consider the perturbed dynamical control system, then one approach to follow is to use some assumption about the disturbance. So A standard way of doing that is to consider that you have an upper bounded disturbance with a known bound. And maybe you can also consider that the available information that you have for feedback control through your sensors, communication links, and other means is also bounded, it's also upper bounded with a known bound with respect to the true value. So we try to think now how we're going to extend the QP design in the case where maybe we can also have dynamic obstacles. So think of maybe many robots moving in the same workspace. They need to avoid each other. They might have constraints of the form, always maintain something like a point of interest to your field of view, which is more like a static safe set constraint. The dynamic safe set would be always maintain your safe distance with respect to the other moving agents in the environment. And we want to do that safely and while reaching your goal sets again with specified times. So the way of incorporating, or one way of incorporating the information that you have about your disturbance in the CBFs and the CLFs can be written down in this form, where essentially we add the effect of the disturbance and the assumptions that we make about the Lipschitz constants of the constraint functions in the condition for maintaining safety for the safe set, which in effect shrinks the effective safe set that we want to consider, okay? Because we're uncertain about the environment, we have to be more conservative about what we think as our safe set. Similarly, we can extend the definition of fixed time control Lyapunov function to its robust version, where again, everything is kept the same, except that we add also the effect of the disturbance and the assumptions that we have made about this disturbance, where in effect that tells us that maybe we'll not be able to reach exactly the goal set, but the neighborhood around that set, okay? And that neighborhood depends on how big this magnitude of the disturbance is. Okay. So once we have these definitions, then extending the quadratic program to take into account these robustness considerations is quite straightforward. So we use this same type of constraints for input, for the time requirements for our goal set, and for the forward invariance of our two sets. Here we have again the static safe set and the time varying safe set. Where all the control barrier functions and the fixed time control Lyapunov functions are tweaked in order to take into account the effect of the unknown terms, okay? The effect of the state estimation error that we consider that we have, and the effect of the disturbance. So solving this problem gives you a solution. We also consider the effect of the other agents, for the time varying safe set. So you can solve this problem, and in order to visualize the response that we would have in a case study of the 2D motion of under-actuated underwater vehicles that have the effect of disturbances being the upper bounded currents and wave effects that apply to them. The control objectives for these vehicles would be to reach goal regions within user-specified times, while keeping a point of interest, like a landmark, always in their field of view. You can think of it as the static safe set specification, and while maintaining a safe distance with respect to the other agents. Okay, so that would account for a time varying safe set. So that would be the results that we get after running the quadratic program for solving with this quadratic program for the trajectories of the robots. And we studied all the various cases, starting from the nominal case with the solid lines here. So you see how the robots are able to navigate toward their goal sets. These are big circles from their initial locations, while always meeting their respective constraints active, which is unfortunately not shown in this in this figure. With the dotted lines, you see the case studies that we ran with one source of disturbance that the state estimation error, and with with the dashed line is the state estimation error, and then with the dotted line we consider both the uncertainty in the states and the additive disturbances, which is the D term that perturbs the dynamics. So the effect of the dynamics is shown here on the plotting of the fixed time control Lyapunov function that shows that in the nominal case, we're essentially able, each one of the robots is able to reach the goal set. But as we add the effect of the disturbances in our control design, and we make our system more robust, but also more conservative with respect to the assumed disturbances, then the robots essentially converge to a neighborhood of the origin that depends, and how far, like what is the size of this neighborhood depends on the magnitude of the assumed disturbances. Okay, so the smaller the disturbances, the assumed disturbances, the closer you can get to your nominal goal set. Okay, so this is one way of treating things. You can consider that your disturbances is something that you can consider an upper bound on it and then try to plan accordingly. That gives you robustness, that gives you ways of maintaining safety, but at the expense of being probably overly conservative. So then the question is, can we do something better than that? And what we have been investigating is how we can use ways and ideas from adaptive control in order to have a better representation and learning of the disturbance on the fly. So maybe now D can be thought as a linear parameterization of this form, where theta is now the unknown vector of parameters that we have to learn on the fly. And delta is a known and bounded matrix. And under the classical assumptions that we use for adaptive control, meaning that the set of the parameters where the parameters might belong is again known, compact, and convex, and that this delta regression matrix can be persistently excited. The problem that we're considering is how to design the adaptive control law such that the parameter estimation error converges to 0 in fixed time in an attempt to reconstruct the true dynamics in a fixed time. And in addition, how to design also our control input such that, similarly to before, the system trajectories converge to the goal set in a fixed time and always remain within a safe set. So I don't want so essentially the main idea here is how you can tune your adaptive control law so that you obtain so you can make your estimation error for the parameters converge to 0 in fixed time. So I don't want to spend time on explaining this filtering scheme that is involved with the adaptive control law. This is just an adaptive control that we borrowed from the literature. But the point is that we tweaked the adaptive control law with this term here, with which I'm pretty sure that you are quite familiar already, that imposes the fixed time convergence of the parameter of the estimation error of the error of the parameters. So we can show that then the parameters converge to the true parameters in fixed time. That is upper bounded by a known bound that depends on those gains here that are properly selected by the user. Okay, so what's the good thing about that? I'll probably be able to explain better with a case study. So we considered the case where maybe you have two obstacles here that are very closely located in a way that creates only a very narrow passage for a robot to move through. So let's consider that we have a robot that is just simply modeled by a single integrator, subject to some additive disturbances that could model, for example, some undulation in the environment. And so we choose our modeling such that this delta matrix here is persistently excited. And the objective is to start from an initial location and make it through the gap or shoot the gap and converge to this goal location that is on the other side of the obstacles. So we implemented our proposed adaptive control law, the fixed time adaptive control law, in combination with our robust QP formulation that I showed earlier. and compared also the performance of the method with respect to other similar work in the literature that has been very vivid and ongoing on adaptive safety and other methods that use adaptive identification through set membership and so on. So what you can see here is that our method, because it learns essentially the dynamic environment in a fixed time, it learns it quickly enough. It makes the robot understand that, well, it is safe to go through the narrow passage, because now this uncertainty bound that we have is shrinking over time, whereas other methods that they don't have this adaptivity, they fail to go through this narrow passage because they think that my uncertainty bounds tell me that it's not safe to go through this narrow passage, okay? And this plot here shows that our approach has good performance characterizations in terms of avoiding the excessive chattering that other methods have. And also here, this figure here to the left shows that indeed the control bearer function over time approaches the safety boundary much closer than other methods are allowed to approach, because we are learning the true dynamics fast enough. Okay, and just let us keep that for the interest of time. That just shows that the fixed time requirement is also met. So starting to wrapping up, we have treated safety in robust control frameworks that utilize control bearer functions and fixed time control Lyapunov functions in order to encode safety and time convergence specifications. We have started investigating how adaptive control techniques can be used in order to reduce the conservatism that inherently come with robust control formulations. And we are also trying to see what's the correct mixing between model-based and model-free approaches. So instead of adaptive control laws, what are the right representations, what are the right means of learning the uncertainty by means of Gaussian processes or reinforcement learning, so that we can estimate the dynamics with confident uncertainty bounds that can be then fed to our controllers. And in fact, how we can even use the control input in order to collect the appropriate observations for this loop to work efficiently and with safety on time, every time. Yep.
Sorry to interrupt, but the time is reaching. So
no, that was essentially my last slide. And if you have any quick questions, I'm happy to answer. So thank you very much for attending my talk.
Yeah, thank you very much for your very interesting talk. We can have one question maybe for posted in chat. By Bahit saying we do not have disturbance bound and state estimation error to be used in the controller. How these challenges can be addressed in your structure?
Sorry, first part of the real one. Yeah. So if the question is that it's very hard to know the upper bounds gamma, then essentially I agree, and that is why we're moving towards other schemes like adaptive control or schemes that will combine some sort of offline training through learning and online adaptation in order to be able to obtain models that are less conservative on the fly.
All right. Thank you very much.
Thank you.
There's another question by Nikolai. Under what conditions can finite time stability be guaranteed in the FXT, CLF, CB, FQB formulation?
Yeah, that's a very interesting question. So because we have the interaction of we have the interconnection with the control input constraints, the conditions are given in explicit closed forms, which I don't know if I even have like a backup slide here to show. So that would be like the effect of if you can find your delta 1 to be smaller than these parameters that again are set by the user, then you know that you will be able to have the trajectories go to the goal set within the constraint with constraint control inputs if they start from this D set here. So all these are long expressions, but they are expressions that involve the sub-level sets of the candidate control Lyapunov, fixed time control Lyapunov function that you have chosen, which is in our case, we use the goal reaching constraint function as the candidate fixed time CLF. I'm happy to send you references.
Yeah, thank you very much. This is great. I'll be very happy to look more into this.
Thank you.
All right, thank you very much, Professor Panagou. And yeah.